Here's the final video lecture that we're going to have on our review material. When we come back after exam 2, we will start working on new information. We'll begin our trig work. So there's just a few things. It's going to seem kind of scattered, just a few different things that I think we need to cover that I haven't quite been able to fit into other lessons so far. So we're going to talk about function variation. We're going to also look at polynomial long division and why we use it. And then we're going to just take a really quick look at rational functions. We've already looked at domains and ranges of rational functions, but I want to take a quick look at those again and use polynomial long division to help us figure out how to graph them and how they're behaving. So first of all, let's talk about variation. Functions can vary directly. One variable can vary directly with another, can vary inversely, or can vary jointly. So direct variation is something that we're really comfortable with. We've worked with it a whole lot. We know what direct variation means. That's when we have one variable, for instance here, y, and it varies directly with x. The one mistake that students often make is we assume that they vary one-to-one, that it is a linear variation always with a slope of 1, and that's not true. If we have direct variation, we can have any kind of a slope, and here that slope for our linear direct variation is called k. So lots of times when you have direct variation, these come in the way of word problems, and so we'll have a word problem and it will give you the setup. It'll give you a value of y with a corresponding value of x, and you use that initial setup to find k. And then it'll ask you a second question where you already know the value of k, where they'll give you one variable and you find the value of another. So direct variation is something that we see quite often. It's fairly common. Here, for instance, we might notice that direct variation could be a distance equals rate times time problem. And here they give us information for our variables, for our independent variable and our dependent variable. We use that information and we find a value of k, and then we can then answer all kinds of questions based on this direct variation function, just knowing the value of k for the whole rest of the problem. I'm not really going to work any examples on this per se. You all know direct variation. You've worked with it a lot. Again, direct variation is going to give you a linear relationship between your independent and your dependent variable. The other variation that we might not have seen a whole lot of is called inverse variation. And this is where your dependent and independent variable vary with each other inversely. So again, it's not a one-to-one inverse relationship. It's not y equals 1 over x. There's definitely a factor of k that can be any real number value. So this is what it looks like for indirect variation. In inverse variation, you might also read inversely proportional. This is another way to turn that statement into mathematics. So you can see from our parent function y equals 1 over x, if we were just to look at what's happening here in quadrant 1, this is definitely the graph of the form of that kind of inverse function. So again, inverse variation, something that we need to be able to turn words into mathematics. Boyle's law is an inverse proportion and inverse variation between different variables, where P is the pressure of a simple gas, V is the volume, and K is the constant of proportionality between those two. Again, these types of word problems, you're going to be given information for the independent and dependent variable in order to find the value of your constant of proportionality, and then you can go on and answer questions based on knowing that value. So the last one here is joint variation. Joint variation is when we have three variables involved. Here, z is jointly related to x and y, or jointly proportional to x and y. We still have that constant of proportionality, so it's not uncommon to have three variables involved in that relationship. Once again, what you would have is you would have information given to you about the three variables involved. You find the constant of proportionality and then go ahead and answer whatever the question might be at the end of the word problem. So here we would say that z is directly proportional to x, but inversely proportional to y. So it doesn't just have to be a multiplication for joint variation, it could be division as well. Here's an example, Newton's law of gravitation. You can see that force is directly varied with your product of the masses and inversely proportional to r squared. So just being able to turn those words into mathematics is going to help us a lot. So you've done polynomial long division before. We've been doing long division probably since 5th grade just on numerals. And then polynomial long division came probably in the form of some sort of shorthand process. But I want us to look at polynomial long division the original way because it helps us turn a rational function into a proper function with into a polynomial with a proper function on the end. So let's look at the process for polynomial long division. Here we have this trinomial and we want to divide it by this linear factor. So we're just going to go back to what we know about our lower mathematics where variables weren't involved, and we're going to look at the process of how we did that just with numerals. And it turns out we're going to do basically the same thing here with our polynomials. So here I have this trinomial. I'm going to divide it by this linear factor. And here's our process. I'm big about process. So here's the process. Write these steps down and you'll never get this process wrong. You'll be able to do it no matter what it looks like under here or no matter what you're dividing by. So the first thing we do is we look at this lead term and then we compare it to this lead term outside. And we ask ourselves, what do I multiply this thing, whatever that lead term is, by to make it equal to the lead term underneath the division sign? So if I want to multiply x by something to make it look like 6x squared, that's going to have to be 6x. So I know that I can multiply x by 6x, and that's going to give me 6x squared. So here's what we're going to do next. We're going to put an open parentheses, and we're going to take this term and multiply it by every term out here. The first term is 6x squared. Then I copy down my minus sign, and it's then 6x times 4, so minus 24x. I put parentheses around it because I don't want to forget to distribute that negative through how many ever terms I might have here. So the parentheses are important. Don't forget that step of the process. So now I have 6x squared minus 6x squared. Those two cancel each other out. Now I have minus 26x plus 24x. So that gives me negative 2x. I haven't subtracted or added anything to the 12, so I just copy it down. Now I repeat that initial process. What do I multiply this by to make it look like this lead term? And so x times what equals negative 2x? Well, that's negative 2. So I'm going to multiply this by everything out here. So negative 2x plus 4. And then I'm going to subtract the whole thing. So negative 2 plus 2x, those cancel, and 12 minus 4 equals 8. So I have a remainder. And here's why polynomial long division is so helpful to us, because we started out with something that looked like 6x squared minus 26x plus 12 divided by x minus 4. We had this rational expression, and now we can completely rewrite that rational expression as this polynomial that is equivalent to 6x minus 2 and then plus 8 over x minus 4. So this is a much more simplified version. It's easier for us to see what's going on in our denominator. It's easier for us to find our domain, for us to find our range. It would actually even be easier for us to graph if we had to. So polynomial long division is definitely something that helps us turn a rational expression. Whoop, don't know what happened. Okay, as I was saying, it helps us turn a rational expression into a polynomial and a proper, much more simplified fraction there at the end. So let's try this one more time again so you can just see the process. I want to make sure that you follow it step by step by step. So we're going to divide this polynomial by this linear factor. So I start out here, I have x plus 2, and I'm going to divide that into 3x to the 5th plus 5x to the 4th minus 4x cubed plus 7x plus 3. And all that goes under the division symbol. So again, the process, I look at the lead terms. What do I need to multiply this by so that it looks like this? That's going to be 3x to the 4th. And then I multiply that by every term that's out here. So I'm going to open my parentheses, put the minus out there. I'll get 3x to the 5th times 3x to the 4th, and then plus 3x to the 4th times 2. So plus 6x to the 4th. And then just continue on down the line. Those cancel. 5x to the 4th minus 6x to the 4th leaves me a minus x to the 4th, and then copy down everything that was not affected by that first multiplication. So again, what do I multiply this term by so that it looks like this? And I'm going to put that right there. So that's going to be a negative x cubed. So that would be minus x to the 4th. Negative x cubed times 2 is minus 2x cubed. Close my parentheses. Subtract. A minus plus. This is a negative 4x cubed plus 2x cubed. Leaves a negative 2x cubed plus 7x plus 3. What do I multiply this by so that it looks like this? That is minus 2x squared. Now I'm going to skip up here since I'm out of space, and I'll just put that here. So I have negative 2x cubed plus 7x plus 3. I'm going to subtract from that a negative 2x cubed, and this times that is minus 4x squared. So those cancel. I don't have a squared term up here, so a minus minus gives me 4x squared plus 7x plus 3. What do I multiply this by to make, or what do I multiply this by to make it look like this? Is going to be plus 4x. Let's give myself some more space here. Oop, wrong one. Let's just clean this off just a little bit so we have some more space. Okay. So what I have now is 4x squared plus 7x plus 3. And we said that we would multiply that by 4x. That gives us minus 4x squared minus a positive 4x squared. And then plus 8x. So those cancel. 7x minus 8x is negative x plus 3. So the next thing I would multiply this by to make it look like this would be negative 1. That would give me a negative x minus 2. So this cleans up quite nicely to those cancel. 3 plus 2 is 5. Now we're near the end of this first video. I think I can finish this up in a second video. So we'll stop here. I'll clean this up and then we'll have a second video over these topics. So look for the next video.